So the purpose here is to walk you through a few different type of problems using Gibbs free energy standard and non-standard. And one of the things I want to show you today is that although we've been using tablature for delta S using delta S using absolute entropies and delta H's using heats of formation, we can also determine delta G using delta G of formations from tablature. So in this problem, they want you to solve for the Gibbs free energy value, the standard, okay? They did give you the standardized values of the reaction and the delta S of the reaction. And this, of course, would come from tablature. They're giving you that. So clearly, to answer this question, I don't have to use tablature, but I'm going to do so. So what I'd like you to do is understand that in your reference tables, they give you the formulas, products minus reactants. This is all considered to be Hess's law, the fact that these state functions of the total change of either entropy, enthalpy, or Gibbs free energy can be gained from looking at the formation of the enthalpy or the Gibbs free energy of formation or the absolute entropy. So we can take the work of other scientists, and because they're state functions, we can treat them to use those calculations and those formulas to get the overall either delta S or delta H or delta G. So in this case, let's do that. So delta G, this is going to be standard because it's from tablature, is going to equal to the summation of the what? The change of Gibbs free energy of the formation of the what? Products. And the reason why it's products is just by what? Convention, so that we keep the correct sign, negative for non-spontaneous, positive for spontaneous, minus the summation of the change of G, okay, Gibbs free energy, a formation of the reactants. I'm writing it there, okay, but hell, that's so easy, it's right in your reference table. So to do this, very simply, like we have done for enthalpy and absolute entropies, we do the same thing. Look at your products first. So I've got two of these, so it's going to equal to 2 times C3H3N is right here. So 2 times 208.6. And what else we have? It's a summation, right? Plus 6 times the delta G of formation of water liquid. Carefully, you look at, I only have it listed as liquid, so who cares? Negative 237. Don't forget your signs. Okay, and then we're going to minus 2 C3H6, okay, which is right here. So 2 times 74.62 plus what? 2 times the ammonia, NH3, it's negative 16.4. If you notice, this guy right here is an elemental state, and just like heats of formation, delta G of formations, if you've got an elemental state, is also 0. So this would be 3 times 0. Trust me, it's 0. And then we're going to come up with the answers. Okay, you can calculate that too, or just follow me. And there it is. There's our answer, just kind of multiplied through here. Make sure you maintain the sign. Same thing here. There's a 2 times negative. Everything else is positive, but then it becomes plus plus. All right, so in any case, we're just going to subtract this values here. And of course, what you get is this number. Okay, so that is our answer. Again, the reason why I'm showing you this is to remind you that we can also, from tablature, get change of G's standard values. Okay, so just to prove to you it's the same thing, you can plug it into your most famous equation to get delta G as well. So let's do that. And there is our famous equation that pops up for us. Don't forget that these are all little zeros here to tell us that these conditions are standard, okay, which not as helpful as non-standard because most reactions aren't, and that's where we're headed here. So let's plug in our values. We have our delta H okay, given to us. So I'm going to prove to you that going through this reaction gives us the same result. So we've got a negative 13.7. Don't forget this is kilojoules. Good habit to write those units in. Minus the temperature in Kelvin. Temperature is 298 Kelvin. But we're going to find out we don't have to be at that temperature. Remember, the products and the reactants both change accordingly with temperature. And then our delta S is given to us to be a negative value, negative 659. This is joule, and this should be actually mole dot Kelvin. And you can see we have an issue. If you look carefully, we did not convert this to joules or kilojoules. So what you could do is times this by a factor, right? And here's what I can do if I don't want to leave this in here and don't want to erase. I can say that there's what? 1,000 joules for 1 kilojoule. So I can just put that in there. Another way I can do, if you want to be fancy, 1 over 10,000 is the same as 10 to the negative 3, isn't it? So I could also put that factor in there as well. So my joules will cancel. This is a kilojoule. All right. No, this is a Kelvin, sorry. That's a Kelvin. The Kelvins here will basically cancel, and you're left with the joules. And when you multiply this through, you get, using those exact numbers, a negative 11,1120.618. Of course, that's in kilojoule, and it's per mole. And that's my delta G. So it's very similar, okay? It's going to be a little bit different because I bet these values are rounded at some point. So nothing is perfect, but if you were to round this to a correct number of sig figs, and if I look at my measured values in my reaction here, it looks like 3 significant figures is my least significant. This would become 1120 kilojoule per mole. And this would become, don't forget the negative there, negative 1120 kilojoule per mole. So you can see, party people, that the rounded result is the same. So they are the same, both fine to do it that way if you have the ability to do so. Obviously on our test, if you had a choice, obviously this method right here is faster, but sometimes you won't have a choice and you must be able to identify that. You can do it through tablature by the basic same way we've been doing it for delta S and delta H. Okay, so let's move on to the next question, question number 2. Okay, and this question is asking, basically, can this reaction here, N2O4, that splits into 2 NO2 molecules, this reaction here, show that it's not spontaneous under standard conditions? Well, I don't have any other piece of data except for my what? My tablature. Now, what I could do is I could find my delta H and my delta S, and then I could put them through my delta G formula, or I can go directly through delta G. So it doesn't really matter. But since A was looking to show delta G is non-spontaneous, I'm going to go through that matter. So delta G of the entire reaction is equal to the sum of my delta G of formation of my products minus the sum of the delta G of the formation, little 0 here, standard conditions of my reactants. Okay, so this is pretty simple. There's only 2 chemicals altogether. So we start with our products, and it's going to be what? 2 NO2s, and NO2 is 51.3. And that's going to be minus just the one product, N2O4, which is 99.8. And we do our math, delta G, standard for the reaction, is equal to 2.8. So we just proved that it is non-spontaneous. If they ask you why it's non-spontaneous, you would say that delta G is a positive value. That's it. You can show that this reaction to prove it's non-spontaneous by it being positive. Now, what I will say is it being positive means that this reaction is pretty reversible. When you're close to zero, have a very small negative, very small positive, that means the reaction is very close to being essentially at equilibrium or just zero. And when you're at small values, reversibility is a possibility. So if you're a little bit positive, that means the reverse is a little bit negative, a little bit spontaneous. So that's important. Now, B is where I'm really after here. Find the temperature at which the reaction becomes spontaneous. This is a classic college question. It's how we use actually delta G all the time. Now, I mentioned in my lecture previously that when you increase the temperature, what you do is you basically increase the motion of the products and the reactants, which means that these atoms that are in their molecules are vibrating, are moving, they're stretching back and forth. And if you increase the temperature, essentially you're making them move more, or the change of them moving more is the same for the products and the reactants. So we would say that the entropy, or the dispersion of energy, is the same for the products and reactants when you increase the temperature. These products and reactants are both in the same reaction vessel. So based on the idea that changing the temperature changes the entropy of the products and the reactants equally, we can actually use other temperatures besides 298 when we're using standard tabulated forms. So the point I'm trying to make here is that if temperature is increasing, we're going to see the entropy of the products increases as much as the entropy of the reactants. And if the temperature decreases and they move less, we're going to say that the product's entropy decreases as much as the reactants. It's not perfect, but it's a very good approximation. It works very well. And let me show you how we use it. So we want to find the temperature. So let's go to our most famous reaction, delta G. 0 is equal to delta H 0 minus T delta S. These are all standardized. So these all can come from standard tables or standard conditions. This does not have to be standard, okay, for the reasons I just explained. So now the question reads, what temperature will a reaction become spontaneous? Well, I can't really calculate that. Here's what I really can calculate. I know that right now the delta G is positive 2.8. Before it becomes negative and spontaneous, doesn't it have to be 0? You bet. So it's got to go through 0. So let's go find the temperature that makes my delta G equals 0. And then I can understand by increasing or decreasing temperature, I can make it move to become negative. In this case, increasing the temperature, okay, should make this enough to go to the negative. So we're going to find the temperature threshold that gets me at 0, and then we're going to look back on the problem to see if we can increase it or decrease it to move it over to the negative side. All right, so we're not directly finding that temperature, we're finding the temperature at which delta G will become 0, and then we'll say anything above or below that will make that happen. All right, so let's do that. Now, before we can do that, party people, we notice something. We're going to have to figure out what the values are of these other equations. We know we're going to set delta G equal to 0, okay, because we're going to solve the temperature. Now, what's my delta H? And what's my delta S? Standard conditions, I'm going to have to go to the tables. So real fast, we'll do products minus reactants. And the products, there's 2 of them. So for delta H standard, we'll do 2 times. This is NO2. And NO2 is 33.2. That's its heat of formation. And I'm going to minus the product, only one of them, which is N2O4, which is 11.1. And when we do that, we get a 55.3. And of course, that is in kilojoules per mole. And that would go here. So 55.3 kilojoules per mole. Okay. We're going to minus the T, and then we're going to have our delta S. Well, delta S, same way. Okay, let's go crazy with gray. Delta S, it's going to be the product, so 2 times. It's okay, and we have, now notice the units here. Oh, bad. This should be in joules. Okay, so this is joule mole kelvins. So this is going to be not kilojoule, it's going to be in joule. So let me just wipe that away. So for NO2, that should be 240 joule mole Kelvin, okay, minus the 304. And I will say again that my worksheet has kilojoule here. It's both joule mole kelvins. So 304.4. So you do the math here, and it's one of them, 1 times that, right? So it's going to be 175, it's positive, 0.8, and that's joule mole kelvins. Okay. Now, I'm going to plug that in here. I'm going to change it to kilojoules for reasons we keep explaining, right? I'm going to times that by 10 to the negative 3 or divide by 1,000. That becomes 0.175 no point there. It's a point I'm not trying to make. 8, and that is, that's going to be kilojoule mole Kelvin. And we solve for T. Now, put T, this is going to be, now, when you think about it, I can rearrange this problem, and so many people can do this mathematically different ways, but let's do it. If I want to make this 0, okay, that means delta H, or I should say T delta H, so T delta S, right, it's a negative value, is going to equal delta H, right? So this goes to 0, and I'm going to move this whole expression, make it positive, okay, and that's why they equal each other. We're going to solve for T, so delta H is over delta S. So that's basically just rearranging that if you want to. Same thing happens here. Okay, I just think it's easier to think of it T equals delta H over delta S. Again, all I did algebraically is I know people hate to see this. Some teachers plus T delta S on this side, plus T delta S on this side. This side is a 0, and that's how I got this. Okay, so when I solve for T, I'm going to put the value in here. And again, you could have solved it this way. Obviously, this would be negative positive T over on this side. So it winds up being the same thing. T equals 55.3 kilojoules. And of course, this is going to be 0.1758 kilojoules. If you look at the units, kilojoule per mole, and this is kilojoule mole Kelvin. And you can see, party poopers, that the kilojoules go bye-bye, moles go bye-bye. You're left with 1 over Kelvin, which becomes a Kelvin. So 55.3 divided by 0.1758 gives me 315 Kelvin. However you want to solve for it, okay? I'm just giving you multiple ways. Now, what does this mean? Is that my answer? No, because this is the temperature when delta G becomes 0. We're trying to make it become negative. Now, think with me for a second. This is a positive factor. Makes sense. One of these guys are becoming 2. So the molecular degrees of freedom are increasing as we go from left to right. So this delta S of entropy should be positive, and it is. Okay, it is positive. So if this expression is positive, okay, then there's a negative on the positive, right? So it's a negative. So we do plus a negative. So the whole expression becomes negative. So to make this delta G become negative, I'm going to need T to become higher. I solve for the T when this becomes 0. It was at 2.8, but now I solve for the temperature when it's at 0. So all I got to do is increase this T. This negative will be big enough to drive it to make the overall delta G negative. So we would say the temperature at which the reaction becomes spontaneous, delta G is negative, would be greater, anything greater than 315. That's how we would answer that. So the temperature would be anything greater than 315 would make this negative. Okay, that's really, really a classic problem. And again, the pitfalls here are making sure our units are correct for our absolute entropies. And of course, understanding that we're setting the delta G of zero, delta G of conditions that were positive into a zero state, solving for that temperature of zero. Now, this reaction, if you think about it, when it becomes negative, when the temperature is high enough, this becomes an entropy-driven reaction. When this positive is great enough with a high enough temperature, it can overtake a bad condition. What are the bad conditions, party people? Well, a positive endothermic reaction is not a favorable condition. Energy is flowing from the environment, so the entropy of the universe is decreasing. And what is a good condition is that the entropy of the system is decreasing as molecules break apart and degrees of freedom are increasing. So if this factor is enough to overtake this factor, it goes. If this overall becomes a bigger negative, when you consider the sign changes here, it can force the reaction to go. This is something that you need to be able to explain. If you can't, you come in and you ask me, but this is an entropy-driven reaction. There's a more favorable condition that overcomes a bad one in this sometimes rule. So let's go on to number 3. So what we're going to do on this side is we're going to calculate non-standard delta G, right? This does not have a little zero. This is non-standard. Get it down. Understand the difference. This means we're going to find the value of the Gibbs free energy when we're not, at standard conditions, which by the way is almost all the time. So this becomes something very, very useful where we can determine whether a reaction has a pathway and it can occur under conditions that are, quote, normal or any other conditions besides these perfect conditions that our tables are based upon. So we have this reaction. Notice the double arrow, which means there's some reversibility to this, meaning the delta G is not going to be so positive or negative in one way. It's going to be relatively hovering around the zero that we just talked about in the last problem. So if you notice in this reaction, or if you notice what we're going to have to do is we're going to have to solve, for the non-standard delta G. Now this non-standard delta G that we've learned, it means that we take delta G, no zero here, and we're going to equal it to standard delta G that we get from tabulated values. And what we're going to do is we're going to add it to our T natural log, or ln if you're cool, of Q. All right, now in order for us to do this problem, we're going to have to come up with our standard delta G and then adjust this part of the equation based upon Q, is going to make some adjustments to that above and below depending if Q is positive or negative. Okay, so we're going to get this, from our tables, which are on standard conditions. We're going to get this Q by products, concentration of products to some coefficient over reactants to some coefficient. Solids and liquids do not apply because they don't have any kind of dilution factor in them. There's no change in enthalpy in a solid or pure liquid. Now, if you look carefully, we're going to have temperature in Kelvin, an absolute value. We don't want a negative temperature to be affecting our changes in entropy or changes in overall direction. And then this R is a gas law constant, that we haven't talked a lot about besides gas laws, but we have talked and used it, in energy forms when we did kinetic molecular theory. So because we're dealing with energy, this has to be in joules. So we're looking for the energy value of this R, and it'll be listed in your reference table, just like this formula is, in your reference table, but it will be in joules. So to start the question, I'm going to have to come up with non-standard delta G. So let's do that first. All right, as we've done several times before, and as this whole lesson today has been about reminding you that you can get delta G from tables as well as using the best formula. So let's just do this fast. Let's take, we have our products, 2 times them. So the products is NH3, so it's 2 times negative 16.4. Pretty easy math coming here, and we're going to take, that's the sum of all the Gibbs free energy of formation of the products minus the sum of the Gibbs free formation of the reactants. Notice the reactants are in elemental states, so they're actually going to be a total of 0. So essentially our delta G standard from tables from 25 degrees Celsius, 298 Kelvin, 1 atmosphere pressure, okay, is going to equal negative 33.32, and that's kilojoules per mole. All right, we've got this value. All right, now we can't continue unless we get the Q. Now, what is Q? Q is equal to the products, and let's go find those products. In this case, we have NH3. They call this a law of mass action, okay, but let's go find it. NH3, and it's going to be to what coefficient? Well, coefficients become exponents, so that's going to be a 2 there. And let's look at our products, our reactants, products over reactants, and then we get this equation from the derivation we did the other day. Okay, and that's going to be to the first power, there's nothing in front, and then we're going to over here, this is going to be H2, and that's going to be to the third power. Okay, because there's a 3 there, even though I wrote over. Okay, so that's our equation. You notice it's going to be unique for any type of reaction we have, depending upon what the chemicals are and their coefficients. So what we know is we basically took a snapshot, that's what a reaction quotient is, at a particular instant in time. What are these concentrations of a reaction that can achieve equilibrium, that has some reversibility? Well, what they did is they measured the pressure. Now, if you notice, I wrote these as brackets for concentration, but and pressures can be in concentration. You can deal with pressure as a molarity, but since these are partial pressures, I'm going to switch this into parentheses as we talked about. So NH3, okay, is right here, and that's my product. So it's going to be 0.50 atmospheres. I'm using parentheses for pressure, but still becomes squared. And we're going to have N2. And N2 is 3 atmospheres, and that's to the first power, times our hydrogen. Oh, I think I got that wrong there. N2 is for the first power, classic Rodsky. Okay, and we have there is for N2 is 1 atmosphere, and that's to the first power there. And then for hydrogen, we have 3 atmospheres, and that's for to the third power. All right, and all I'm going to do there is solve for that 0.50 squared and divided by 1 times 27, or divided by 27, and this gives me 99.3 times 10 to the negative 3, which is equal to my Q. That's my reaction quotient. Okay, so we have our delta G of standard conditions. We have our reaction quotient, which, by the way, is a dimensionless number. Okay, these are atmospheres, but they all cancel. Now we just got to get our temperature, which we're going to assume at 298. That you're saying it's a 298. It doesn't have to be, as we've talked about. And then we have to get our universal gas constant. So we're ready just basically to plug this in to find what's happening here. So let's just rewrite the equation. Delta G non-standard is equal to delta G standard, okay, plus, okay, RT natural log of Q. Okay, so our standard delta G is negative 33.32. Okay, that's in kilojoules. We're going to add that to my R. Now my R, okay, is given to me as 8.314, and that's a joule mole Kelvin, which is basically the same kind of unit as an entropy, and we're going to have to adjust that value. Okay, so we're going to times that by 10 to the negative 3, or we're dividing by 1,000. It's a negative. It's the same deal. By dividing by 1,000, I'm converting it to what? Kilojoules. So this becomes 0.0083 0.314, and that's going to be kilojoule, okay, mole Kelvin. Okay, so I just divided by 1,000 to convert my R into kilojoule units. This, of course, is in kilojoules as well. Our temperature is 298 Kelvin, but that could be any temperature, as we talked about. And then a natural log of our Q, which in this case is 9.3 times 10 to the negative 3. Now I want to stop here for a second and make some sense of this. Look at our Q. Our Q is less than 1. We get a number less than 1, the log or natural log of a number less than 1, this expression right here is going to go negative. And that negative is going to make this whole number negative, which is going to be added to this negative, which means our delta G is going to become more spontaneous. You must understand that. Forget just the math. This is important. Why? Look at your Q. Who is a much larger value? There's a lot more what? This is products over reactants. We have a lot more reactants. Okay, so we've got a scenario where the reactants are bigger than the products. So if I've got a lot more reactants, doesn't that mean the reactants are going to collide more often and produce more products? Yes, that means there's going to be a huge pathway to go forward if most of your molecules in your reaction vessel are reactants. They're going to collide more often, therefore react in this pathway. So it should make sense that I'm going to have a shift in equilibrium if we're talking Le Chatelier's principle to the products, which means my delta G, which is always measured for the forward reaction, is going to become increasingly more negative. That's important, very important. So let's go find that number. Okay, so we plug it in, and when I do that, I get negative 44.9, and my units are kilojoule per mole always. Everything should cancel in this process. Kelvins go bye-bye. Okay, this is a dimensionless unit, and these are kilojoules. So if you notice, we started at negative 33.32 kilojoules. Now we're even more negative. We're even more spontaneous. The pathway's larger when we have a snapshot in time of reaction when there's more reactants. How do I know there's more reactants? The Q is products over reactants. Okay, so I hope you can see that. Not just be able to do the math, be able to explain why the math gives us what it does. We're really using this reaction now. This formula is really an application or really a quantitative value of Le Chatelier's principle that states reactions will become more spontaneous in the forward or reverse if you change the concentration. The key is Q. Changing the concentration of products and reactants will make your non-standard G become more spontaneous or less spontaneous for the forward reaction. Okay, hope that helped.